This is Mr. Sand, and I'm going to talk to you about the first law of thermodynamics. Okay, so thermodynamics is something that's a very tricky kind of topic. We're just glancing it right here. We're barely touching thermodynamics, but we're just going to give a very simple overview. If you're interested in this, because it is an interesting topic, I totally recommend you go into more detail of this. There's plenty of videos that will walk you through some of these ideas and walk you through some of the reasoning behind all of these kinds of these formulations. But for now, all we're going to do is we're just going to define the first law of thermodynamics, and that is this right here. It's going to be delta U equals Q minus W. All right. So delta U, I say in the workbook that delta U is, or I say this in the text, I say that it's the change in thermal energy. Well, yeah, but that's not exactly correct. Thermal energy I equate with internal energy. We can say they're kind of the same for our purposes here, but in reality, this is the change of internal energy. So when I'm saying change in thermal energy, I really mean change in internal energy. And this is the energy you get from all of the kinetic energy of all the molecules involved and all the atoms involved and so forth. Q, of course, is heat. So that depends on if the heat's going into an object or out of an object, but that's heat. So that's energy going in or out of something. And then finally we've got W. W? What? W? W is work. This is awesome. So work's involved here. This is crazy. Work is popping up here. So this is work, but it's a very specific kind of work. It's work, if it's positive, then it's work done on the system. On the system by something else. I gotta double check that real quick. And it's negative if it's work done by the system. By the system. And remember, heat is positive if it's work, or I'm sorry, heat is positive if energy goes into it. If energy in, negative if energy goes out. Goes out. Okay, so we've got our definitions all lined up here. For our problems that you'll run into today, we're going to set this this internal energy equal to 0 in all the circumstances. So you don't need to worry about the change of internal energy. We will assume that there is no change of internal energy in any of these systems. We'll assume that they're completely isolated. There's no way to change the internal energy of the system. So there is no change in energy for all of these problems that you'll see. So all you'll do is you'll say, okay, well, this is a great equation, but overall, that is just going to equal 0. It'll equal 0. So it'll be 0 equals Q minus W. And you'll either be given this or that, and you'll have to find the other one. And these positive and negatives right here are very important with this, obviously. Because you're going to get very different numbers. Now, remember what the units are here for heat and for work. The units for work are Newton meters, and the units for the heat is joules. And Newton meters, it's real quick right here. Let's just look at what Newton meters are. Do you remember what Newton meters are? Newton meters. Let's look this up. What do you see right here? Newton meters. Okay, is a unit of torque. Sure, it's that. It's also work. It's gonna be. Oh my God! It's a joules. Wow! Wow! I hope you remember that. So let's look. Let's put that up there again. Not Skype. I don't want to do Skype. Quit Skype. Okay. So both of these are in units of joules. So this will be in unit of joules as well. Joules as well. So these units are really easy for us to work with in this section right here. Okay, really quick, I want to describe something to you that this is a practical use. When we use let's say like a car, you've got the car. I don't know if you knew this, but the car is producing a lot of like a little mini explosion. So the car, in every little cylinder in a car, you're producing a little explosion, and that explosion, that heat is used to do work. That heat, what it does is it forces this that explosion. The heat forces this piston down. Let's draw a little piston for you. So here's like a cylinder in a car. It's actually a cylinder, and inside here is a little piston. Looks like this, and you'll be seeing drawings of this over and over and over again if you look online. I'd say it's a little piston, and this explosion, this heat will drive that piston down, so that that heat will do work, which then this will then be translated into other motion and blah blah blah. Your cars move, and you listen to your favorite music while you're in the car. So that's an instance of heat doing work for you. So you get work out. That heat is then drained, of course. Drained is a weird way of saying it, but the heat is lost. It's sucked out and it's put out into the exhaust, and then a new little squirt of gasoline comes in here, and then it gets exploded, and that it produces heat, which then drives more work, and then your car keeps on going. But this system can also work in reverse. You can also use work to take out heat, which is pretty cool. That's what happens in your refrigerator. Your refrigerator. Another thing is this little system right here. Let's see. So let's pretend this is a box where you put your food. So you put your food in this box, and there's like these little. You might notice in the refrigerator there's these little coils in the back. Or maybe there's just a little box in the back. You can definitely see this in the freezer. There's some sort of coil there. What happens is that these coils that are wrapping around here, they're like little tubes, and they lead into this little compressor. In the back of your refrigerator, you notice that there's a little motor running. So there's a little motor. That little motor does work. It does work to compress gas. So you've got gas in these little tubes. This motor does work on it. It compresses it into liquid. Then that liquid comes up over here, and your food, the heat from your food, then vaporizes this liquid into gas again. So it goes, let's just rehash that. It was in gas, and then it goes into the motor, which it compresses. It does work on it. Work. And then since it compresses that and does work on it, it turns into liquid, and then that liquid then absorbs the heat. So then the work is put in to take away the heat. It's pretty cool from your food. Eventually, this motor it doesn't just work in a complete vacuum over here. This motor does obviously do work, and it takes energy to do that. So you can feel all of the excess heat that it produces from doing that work. Yeah, I think that's all I want to say about that. So what? So what's the big deal? The main idea I want you to, again, to look at is this. This is the first law, and we'll do a couple problems right now. So